Good morning. Welcome to Parametrics' webinar series of meters classes, meter schools, due to our COVID-19 experiences. Today's class is Justification for Meter Site Testing. My name is Phil Fischbach. I'm manufacturing mechanical engineer here at Parametrics, and I'll be walking you through this class today. So what we're doing today, we're doing Justification for Site Testing. Today we want to discuss the parts of a meter installation that can lead to incorrect billing. We want to talk about test methods to catch these problems in the field, and we also want to look at some real-world examples. So sort of in a nutshell, we're going to sort of summarize what we've had in these past few classes, but more than that, we want to talk about why these classes, why we do what we do in checking not just the meter, but the entire installation. So let's start here. What are the costs of site testing? Well, there's the cost of personnel. The person, himself or herself, that's going out to test these various meter sites. They have pay and insurance and all the things that goes with employees. There's the vehicle, and there's the gas, there's maintenance. There's the equipment cost, the tools that you need to do the testing. There's the training cost, whether it's a webinar like this, or if you were to come here to get training, or if someone comes there, the time that it takes. All of this added together is easily a $100,000 investment. Well, that's a high cost. But consider the other side of it. What are the costs for not testing your sites? Let's consider a typical transformer-rated metering installation. A typical transformer-rated installation consists of all of these things here. You have the meter itself right here in the red block. And we test at these points here for your voltage switch and your current switches. That's where we test. But that's not the only thing involved with a meter site, with a meter installation. Remember that the meter only meters what the meter can see. So if there's something wrong outside of the meter doesn't care. The meter doesn't even know. The meter only reports what it can see. So for instance, if the meter normally sees, let's just say 5 amps, and now it sees 2 amps, it doesn't raise a flag and say, hey, I used to see 5, but now I see 2. It only says, I see 2 amps. And it sees that at these measurement points. This is where we hook in, where we want to measure. But what about the other things at the installation? What about the voltage transformer? What about the current transformer? What if there's something wrong there? Does the meter see that? Does the meter report that? No, it doesn't. What about all the switches and wiring? What about your voltage test switches? What about the wiring in between? What about the current test switches? What about the wiring in between those? Look at all these points where there's some kind of junction. None of those things normally get tested, and the meter cannot see that. But what if you could see all of it? Well, with our test equipment, you can. And this is why we test the entire installation, because there can be problems in all of these places. So even if the meter is perfect, the billing may not be correct. Sources of billing errors include a bad CT. It could be overburdened or shunted. It just might be the wrong accuracy class, or the CT itself. Maybe it's worn out. Same thing with the PT. It could be bad. It could be overburdened. It could be the wrong accuracy class. What about faulty or incorrect wiring? For instance, a loose connection, or maybe a too small wire, which would increase your resistance. What about the meter is not accurate under the actual customer load conditions? So in the lab, it tests out just fine. But out there in the real world, there's something affecting the meter and it's not measuring properly. What about clerical errors, or what about theft, especially now as our world has changed for the past few months and money is getting tight in so many areas? People are going to start looking for ways to reduce their costs. And if they can get free power, they might try to do that. Well, here is a scenario that was studied. There was a 3-year study from a a municipality that had 35,000 transformer-rated installations. And over the study, there were 6 areas of error that were found. There was administrative error, wiring error, a faulty meter, theft of service, and CT problems and PT problems. I'll give you a second to guess. What do you think was the greatest error? What was the least? And so on. Well, as the study revealed, we found wiring errors were 19% of the problems. A PT was 7%. Administrative error was 37%. So administrative error, that's something like somebody somewhere along the line copied down a 3 as a 5, or a 5 as a 3, or a 1 as a 7, or who knows what, but there's an administrative error. There's a faulty meter, was another 19%. A CT problem was 7%, and theft of service, 11%. So during this 3-year study, the total problems found after only 10% of the sites tested were 96 problems. So 96 divided by 3,500, which is 10% of the 35,000 meters, came out to 2.7%. The total lost revenue found, $2.2 million. So the average lost revenue found per problem, just an average, $23,000 per problem. Well, when you look at that, remember when we said the cost to do the testing, when you have your personnel, you have your equipment and so on, was over $100,000? Well, at this average, you would only need to find 4 problems, and believe me, you will find 4 problems, would easily pay for your investment. So at Parametrics, we have an integrated site test philosophy. There are 3 aspects of this that we want to test. So step 1 is the site analysis. Step 2 is your instrument transformer testing. And step 3 is your meter testing. So we don't want to skip the meter. It's just that there's more to it than the meter. So the first part is the site analysis. In the site analysis, you want to do your homework. You want to know what it is you're testing, what form would I expect, what service type before I go into the site. I want to know the correct vector diagram and to be able to check it on the site and to know what kind of wiring to expect. And the services that we look at, there are 4 main services that we're going to examine. There's a 3-wire delta. In a 3-wire delta, you might remember from the class I taught a few days ago, you get 240 volts from phase to phase on all the phases. There's also a 4-wire delta. The difference, of course, is that a 4-wire delta has a neutral tap, except it's not centered. It's between phase A and B. And this gives us some unique properties that we can take advantage of, where we have different voltages from phase to neutral or from phase to phase. A 4-wire Y also has a neutral tap, but it is center tapped. And so I get 120 from phase to neutral, but 208 from phase to phase. An important thing to notice about this one is that phase C is not utilized. And then, of course, there's a single phase. In the single phase, I get 120 from phase to neutral and 240 from phase to phase. So this side of it is a little bit easier, but our metering choices is what makes them complex. So a vector diagram is the tool we want to use that shows us so much information to know if there's something wrong at the meter site. In a vector diagram, I can see my voltage amplitude on phase A right here, the open arrow, my voltage phase, that is in voltage on phase A, it's on 0. Phase B here is at 120, and then phase C at 240. I get my current amplitudes and current phases with the closed arrows, and I get my phase relationships. So I have my relationship between my phase A voltage and my phase A current. In this case, they're in phase. But I can also see my relationship from phase to phase, from A to B and from B to C. So if we know what we should see, then I also am able to see any problems. Here are some examples of some vector diagrams on common meter forms. The first one here on the top left is a form 5S meter. Now, I'll be honest with you, it's kind of strange that this comes up today because it seems like about the last 2 or 3 meter schools where I was teaching, every question had something to do with a 5S meter. And it's very common that 5S's raise a lot of questions, and the reason is because phase B is used as a reference, and it gives you this strange looking vector diagram. However, this is normal for a 5S. On one side you have a lagging phase, and on the other, or lagging relationship, and on the other side you have a leading phase relationship. It's because phase B is your reference. Here on the top right we have a 9S vector diagram. Notice that the phases are not equally spaced. They're not in an equal relationship. Again, this is normal. Phase A goes to the right, phase B goes straight to the left. But your currents are in an equally spaced relationship. And in form 6S, you have something special. You have 3 phases, but what happens is this meter, it's called a 2.5 element metering situation. And so one element is assumed. And what that means is when you're looking here in this connect view, you don't see voltage B. It's assumed. And we'll come back to this in a second. And then on a form 9S, a very common meter, everything is equally spaced. Now back to this 6S for a minute. In this 2.5 element meter, you have this connect view, but you also can get this meter view. In the meter view, now both of these are correct, but what happens is in the meter view, this is the mathematical view. And so this is how the meter calculates your kilowatts. But it doesn't mean it's wrong. Oops, I meant to back up there. This view is what you're going to see on your 3 series with your equally spaced vectors. But you just need to know that on the meter view, this is how the calculations are made, and it has to do with being a 2.5 element meter. So this class is not one that goes into the depth of why that is like that, but if you have questions, you can always come back and we'll be glad to give you further teaching about that. So here's a good example of being able to utilize a vector diagram to see what is wrong. So here we have a 9S vector diagram. Right off the bat, you're able to see a couple things. One of them, notice that we have this full color vector diagram that you have on all our Pyrometrics equipment. Another thing you'll notice is that the current vectors are all different lengths. My amplitude are different. So on phase A, I have 3.2 amps. Phase B, I get 2.2 amps. And on phase C, only 1.6. So something is wrong that my currents are all different. But the bigger thing is look at this phase relationship between voltage A and current A. They're opposite of each other. Well, what could this mean? It would mean that phase A CT is reversed. Maybe the CT was installed backwards, or maybe the wire is driving in the wrong direction. Maybe it's wired backwards. So polarity is a big deal. The polarity of the connection matters. The wrong polarity means a totally wrong metering. Now keep in mind that even though it's backwards or it's wrong, the lights are still on the other side of the meter. Everything is working normally on the other side. So when the power factor is not equal to 0, reverse polarities may not be so obvious. So what does that cost us? Well, remember that my watts are equal to my voltage times my current times my cosine theta. Okay? So the theta is my angle between my voltage and my current. So cosine of 180 on phase A makes negative power. So that means that the reading that I get from that meter, even though the meter is working correctly, the reading will be 66% low, assuming a current load. So that means for a $1,000 per month bill, the loss would be $660 per month. That would also mean, the converse of that is that out of $1,000, I'm only getting $330. I'm missing 2/3 of my bill because of my phase A current going backwards. Why is that? Let's look at the math. We'll assume 120 volts on all phases, 5 amps on all phases. My theta for phase A is 180 degrees, but for B and C it's 0. Well, cosine of 180 degrees is -1, okay? Cosine theta is 0 is +1. When I do that, I get 120 times 5, 120 times 5, 120 times 5 on all phases. However, on phase A, it's times -1. Well, this -1 is going to cancel this +1. That leaves me only one positive. -600 plus 600 comes out to 0, plus 600 is only 600 watts that's getting metered. But the actual meter power is 1,800 watts. So I'm missing 1,200 watts. So that's what a backwards CT could cost me. What about this one? What do you see right away? Well, again, my currents are all different values in amplitude, but even bigger, where's my alignment? My voltage A seems to be aligned with current B. My voltage B seems to be aligned with voltage A, while phase C looks normal. Well, this could be an example of CT A and B are swapped. So what does that mean? Well, again, you have to take into account the cosine theta. So if I have 120 degrees on phase A and B, so what that means is from voltage A to current B, this angle is 120 degrees. And then the opposite for B and this current. This angle is 120 degrees. Cosine of 120 degrees on phase A and B makes negative 50% power on each phase. The reading will be 0 watts if you assume a balanced load. So what that means is that for a $1,000 a month bill, the loss would be $1,000. So if it's 1,000 out of 1,000, how much is left? 0. When I add up my voltages at 120 and my currents at 5 amps, and I get my phase angle for A and B are both 120, but C is 0, cosine of 120 is negative 0.5, cosine of 0 is +1. So I get negative 0.5 adds up to -1. +1, what does that add up to? -300, -300, +600 equals 0 watts, even though the actual meter power is 1,800 watts. So why do we do the site testing, the installation testing, not just the meter? It's because even though the meter is working properly, I'm billing 0 watts, even though 1,800 watts are passing through that meter. Why is it? It's because of that phase angle. So another thing is bad wiring on a current circuit. A faulty connection can easily add a few tenths of an ohm in burden. There can be improper wiring. So that's not just bad connections, but maybe the wrong gauge wire or the wrong direction, missing grounds, or even multiple grounds. So almost all wiring errors result in a reduced billing. So this is the kind of thing we want to be on the lookout for. And it could be as simple as turning a nut or a screw one more turn to get a good connection, or making sure that the leads of that wire are connected to the right points. Bad wiring on a voltage circuit can reduce the available current to the meter so it doesn't have the VA necessary to operate properly. So the current drawn by the meter reduces the voltage seen at the meter. Okay, so let's look at this example. For 50 feet of 14 gauge wire to the meter, our normal burden would be, get 120 volts supplied, 0.2 amps, and a resistance of R1 and R2. That means resistance for my wiring to the site and back, of 0.036 ohms. So that leads to 0.0075 volts, which is a 0.006% error. Okay? Now consider a bad connection that increases my resistance by 4 ohms. So the voltage is still 120, my current is still 0.2, my resistance 1 and 2 are still 0.036, but I need to add in the 4 ohms due to a bad connection. That adds up to 0.843 volts, which is 0.7% error. Not 0.007%, but 0.7. That would be an increase of $7 lost on a $1,000 a month bill. Now, on one hand, you might say, well, $7 isn't much, but the reason that $7 is just a bad connection. What if you have a bad connection? How common would a bad connection be on every site? That would be a relatively common problem. It doesn't take much to have a bad connection. So what if you lost $7 on every site? That's going to add up very quickly. The second thing that we want to look at in our integrated site test philosophy is my instrument transformer testing. So I want to do a CT direct burden measurement and a ratio test. Same thing with a PT, a direct VA measurement and ratio test. And I want to look for waveform and a harmonic analysis for saturated transformers. So CTs, there are a lot of things to consider with my CT. One thing to consider is my CT accuracy. There are 0.15 accuracy rated CTs, 0.3 accuracy rated CTs. And then when you get below 10%, you lose accuracy. There's the effects of burden, there's the rating factor, and there's extended range CTs. Now, extended range CTs are really fascinating. They're somewhat taking over the market because they can be utilized in so many different situations because the range of the CT maintains its accuracy even at lower currents. Errors with instrument transformers. One of them can be a shunt problem. If you leave the shunt in the wrong position, it produces incorrect readings. Now, it doesn't produce a 0 reading, but it produces a low reading. And I won't name any names, but I do know of a situation that happened in a state near Tennessee. And what happened is some work had to be done at a particular site, and one of the CTs was not completely opened when they left the site. And it went on like that, and finally some numbers came up that gave them reason to go back and check that site again. And they went back and they found that one of the shunts on one of the CTs was not quite all the way opened. And so that little bit of contact on that closed CT led to a dramatically lower reading for that meter site. And they lost a lot of money. It wasn't the customer's fault. It was just a problem on a shunt was closed. So that's something to be careful of. Now, why do you need to be careful of that? Well, you already know. Whenever you're going to that CT, before you do any work, before you pull anything, for safety's sake, not only are you wearing all your PPE, but you need to make sure that shunt is closed so that you don't have an accident. You're probably familiar with the CT bathtub curve. Now, here's a great place for me to pick on one of the bosses here, because Chris gave a perfectly boring class last Tuesday. I hope you didn't miss it. It went kind of like this. This is a bathtub curve. You want to stay at 100 to 400%. It would have been so much better had I been teaching that day. I can teach your, I can keep your attention, and maybe we can have some jokes and all kinds of things. And be sure and fill in your comments there in the chat box. You can make the request for Chris to never teach again. But anyway, back to the curve. What's really important about CTs is that you always want to operate on 100% or better, because these are how the CTs are rated. So notice on your CT curve, see these red lines. Okay, so this red line, this vertical line, is at I'm at 100% load, and so that's where the CT is rated. That means at 100%. So when I have my rating factor, let's say it's 100 to 5 CT and I have a rating factor of 4. That means that CT keeps its rating factor up to 4 times the current. So in this case, that's why it goes up to 400. So it meets my accuracy spec from 100 amps all the way up to 400 amps. But look what happens when the CT reaches saturation. When I go over 400 amps, look at that curve. Over here is my percent accuracy. My accuracy goes right out the window. My CT is saturated, and my accuracy goes out the window. My meter is giving me all kinds of bad numbers because the current that's running has all kinds of problems with it. But look what happens going the other way as well. If I get below 100%, I no longer hold a 0.3 accuracy spec, but now I have a 0.6 accuracy spec. And I can only hold that for so long. And then again, my bathtub goes straight up. My accuracy goes out the window. So I really want to operate my CTs at 100% or better. Now, what we're going to find out soon, and what you may already know, is that CTs and PTs are very sensitive to temperature, and we're going to find out more about that. The temperature adds resistance, my burden adds up, and so I can lose accuracy with my CTs due to temperature. Let's look at bad wiring on a current circuit. Using too small a gauge wire can result in overburden on my CT. So if I have 50 feet of 14 gauge wire, which is 0.14 ohms, this is more burden that is allowable for a 0.1B class CT. If I use 50 feet of 12 gauge wire, that is 0.09 ohms. So on a 0.1B class, that means I need to be under 0.1 in my burden to keep my rating, okay, to keep my accuracy. So as long as that 0.09 is under 0.1, then I'm within spec. But the 0.14 is over the spec, which means there's too much burden on that CT. So this 0.14 burden is more than's allowable. The 0.09 is within the burden allowable for 0.1B class CT. So that means that without any bad connections or any other problems, using too small a wire size can ensure you get the worst performance from your CT. Now, why would that happen? Who knows why? You're out there, you're putting in a new installation, and for whatever reason, you ran out of wire. And so say, okay, well, we got to get this thing up and running, and the customers need this. We need to get billing on this site. And so we'll use this 14 gauge, and we'll come back later, and we'll put the 12 gauge in it, and everything will be fine. But as it happens, you never get back to it. It gets lost in the busyness of work. And so that 12 gauge wire, that 14 gauge wire remains on that site for a period of time, and we're getting bad readings because my CT is overburdened. Maybe something like that. Well, a direct burden measurement is another tool that you want to use for your site installation checks. And so a direct burden measurement measures voltage and current on the CT secondary and uses Ohm's law to get a specific burden reading. So why this is important is because you're getting a direct reading on the site live under operating conditions. And so you remember that V is equal to IR, or voltage is equal to current times resistance, and that becomes resistance is equal to my voltage divided by my current, or that is my burden is equal to my voltage divided by my current. And so this is what it would look like on a 3 series screen. You'll hook up all your equipment, and you'll notice that over here on the right side, I'm measuring on this particular CT, I'm measuring 0.2 volts and 2.5 amps. And that's approximately the same on all 3 phases. When I do the division, that comes out to 0.0795 ohms of burden, 0.08 and 0.08. So in this situation, then that would come out as a pass. This is telling me that I have the correct or an allowable amount of burden on that CT if it's a 0.1 class. So direct burden measurement can be used on sites with as low as 1 milliamp on the secondary. And it's the preferred technique over added burden because it gives a direct answer rather than a burden range. So the direct burden measurement can also be used to help troubleshoot loose and intermittent connections. So that is to say that when you go back, if you had a loose connection, some of these numbers might not be right, and you'll find that you have a higher than allowable burden. So here's another chart to look at a burden class of a 0.15S, and these are sort of a precursor to the extended range CTs. So notice that I'm at 100% all the way up to 400%. I'm within my accuracy allowable range, okay? Right here is my actual curve. And notice that even as I drop below 100%, I maintain for an extended range on these 0.15S CTs, I'm able to maintain my 0.15 accuracy all the way down here in 10%. We want to thank Kent Jones at GE for this particular example. So how do I do that? Well, with a CT ratio with burden testing, I want to do ratio testing is a preferred approach when we gain access to the CT primary. So then what we do is we measure on the primary and we measure on the secondary at the same time. And so here we can use a flex probe, like is in this example, installing the flex probe here, and we can also use high voltage probes. Here's an overhead and here's an underground where we use the safety stick and we put the high voltage probe in those situations. So that's how we get our primary. The secondary, of course, comes right at the site. It's made on the test switch, and the advantage of this is it's the same connection that is used for the rest of the site testing. So you don't have to move anything, and you're in a safer situation. So the ratio testing and burden analysis is the most accurate and complete approach for testing at the CT in service. And that's the real advantage, is you see what's happening while it's working. So the CT testing can be done with a very high accuracy. So what we want to do is we look at the nameplate ratio as a 250:5, and when we measure the high side and the low side, we're getting 249.99 and 4.99. So that comes out to 250.02. And so in this scenario, this comes out as a pass on all three phases. The other thing about this is that you're able to look at these other diagrams, and you can see that the CT installations can be fully verified in the field. And you see that it maintains accuracy, and then it suddenly falls off in your ratio error. And then as you get outside the range, you get secondary current change, same thing. And when you use your parallelogram, all of this comes from Chris's class. You might remember, you may have been asleep at this point when Chris was teaching, so this is just a reminder. And then when you get outside the your parallelogram, again, you lose all your accuracy once you get way outside the chart here. So we can verify that the ratio is correct and constant as the burden changes. If you get too much burden, then you lose your accuracy. Now the CT rating factor, this is the most misunderstood spec. The rating factor has absolutely nothing to do with burden. If a CT has a rating factor of 4, that means that at 30 degrees C, which is the same as 86 degrees Fahrenheit, it can be used up to 4 times its label current and maintain its accuracy class. So that is, if it's 100:5 CT, like we said before, 4 times 100 is 400. So it could be used up to 400 amps at 30 degrees C and maintain its accuracy class. But look at this chart for a minute. Now this This is important, especially if you're in hotter places, like say you're in Arizona or southern Texas or down there in southern Florida, the places where it gets very, very hot. Or you're in a pad mount where you have all these CTs and they're inside a box and there's nowhere for the heat to go. Okay? Look what happens to the rating factor. The rating factor is a strong function of temperature. Okay? If a CT has a rating factor of 4, it means that at 30 degrees C, it can be used up to 4 times its label current and maintain its accuracy. But what if it doesn't stay at 30 degrees C? What if it's in a box? What if it goes all the way up to 60 degrees C? Okay, let's look at this. Here's an example of a CT with a rating factor of 4. Okay, so that would mean at 30 degrees C, we'll follow that line all the way up to 400 amps. Okay, so again, it's a rating factor of 4 on 100 to 5 would be good for up to 400 amps. So that's how we got to this point. But let's say it's in a box and it gets up to 60 degrees C here. Let's follow that line. If you look, that same CT drops from a rating factor of 4 to a rating factor of 3 right here at about 55 degrees. See? It's only good for up to 300 amps. Okay? So that means if I have that 100 to 5 CT with a rating factor of 4, but I place it in a situation that the temperature is much higher than 30, and in this case we're looking at 55 C, which is 140 degrees Fahrenheit, and you know in some of these places, in some of these situations, we're getting up to temperatures like that and higher, then you know that that CT, you can no longer rely on that CT at 400 amps because the temperature is too high. It's only good for up to about 300 amps to keep it and maintain its accuracy. So PTs have a very similar situation as CTs. And it is another low accuracy item in the chain at an installation. It's a 0.3% is the basic accuracy, and the accuracy again decreases rapidly with burden. So with potential transformers, when we do this testing, again, I'm looking at a measured ratio. So my nameplate ratio is a 4 to 1. On my primary volts, I'm measuring 454. On my secondary, I'm measuring 114. When I do the division, that comes out to 3.99, which is within my allowable limit for a 4 to 1 ratio. So in this case, all 3 PTs pass. But what about an overloaded PT? If I have an undersized PT, it can lead to overburden situation and a waveform distortion, especially with high-end meters. So what happens is this yellow wave right here that peaks out, stands out by itself, is my PT output. But the blue, this blue garbage that's all over the place, this is the current being drawn by the meter from this phase. Look what happens to this, all kind of junk. How do you think the meter is going to see that? It's going to be bad. And so the third step on the integrated site philosophy is the meter testing. I want to do a customer load test. I want to do a phantom load test. And I want to do accuracy under harmonic loads. Okay? So the fact that a meter is accurate in the lab does not mean that it is accurate in the field. Why is that? Because out in the field, you may have harmonics. Out in the field, you have rapidly changing loads. Out in the field, you have power factor variations. You see, in the lab, we only test for certain conditions. But we know that out in the field, we have far more conditions than we have in the lab. Why is this important? Because if you go back to where we started, the meter can only meter what the meter sees. The meter can't see everything, and the meter is under a variety of conditions. And so whatever the meter sees, if that changes and that has so much variety, then that's how it's going to meter. Does it still meter correctly under all those conditions? So all of these things are things that can affect the accuracy. So in the integrated site test philosophy, for a customer load test, we want to look at the real world conditions. We want to see the voltage and the current harmonics. We want to look at current and phase angle relationships. Are they balanced correctly? What about a load box test? On a load box test, we do ideal current and voltage waveforms. We do an ANSI test that involves a full load, a power factor, and a light load. We do customer test sequences for special applications. So when we do all of these different tests, a customer load test as well as a load box test, we get a really good look into the meter and if we're getting good measurements, if we're billing correctly on this particular site. So with a customer load meter test, a watt-hour test, what do? Well, we're going to test for the pulses under the real-world conditions. So we get our watt-hours, our VA, and our VARs, and from this we get a certain registration. So in this case, we got 100.015% registration. So I would estimate, looking at these numbers, this one was probably done in a lab because that's a pretty good registration. And different places have different allowable limits for those for your percent registration. Where we are here in Tennessee, we fall under the TVA area, and TVA allows a plus or minus 2%. So that could be 98 up to 102% registration. So we consider that to be a pretty wide range. I think it might be the case where you are that you would think that's extravagant, and you might have a lot tighter range that's allowable. So we want to look at that percent registration. How many pulses am I getting to measure my watt hours? We also have the ANSI test. Under full load, what we're looking at is a full voltage, a full current, and a proper power factor. Then we'll do a power factor test. So we change the power factor. We have a full voltage, a full current, but the power factor, look at it, is only 0.441. We adjust the power factor on purpose to see if the meter still measures properly. And here it was at 99.9%. And then we do a light load test. In that scenario, we have full voltage. I'm having trouble saying voltage. We have a full voltage of 238 volts, or call it 240 for the sake of argument, but a low current. It's 10%. It's 0.497 in this case. And the power factor is back to normal of 0.896. Is the meter still measuring correctly when it has a low current? And so in this particular test, we got 99.9% accurate in all the different ANSI tests. And so we would say that this one is a pass. So, here's another thing you might want to know. As far as what's pass or fail, this is something that you can set in your 3 series. So you can change, and when you're using your 3 series, you can go into the user preferences, and you can set it to say that my pass-fail limit is, for instance, 99.5% or 99%. And then when you do that, then this box right here that's yellow, it'll be either green or red. And it will say, right around here, it'll say pass or fail. So that's a feature that you're able to do on the 3 series or even the 7 series also, to help you out in the field, to get you an immediate answer of for some reason I'm getting a bad reading on this meter. And it may allow you to go back and look at the meter itself, or to go back and look at some other tests like we already examined, like a CT ratio or a burden test or a PT test. Or we may go back and re-examine our vector diagrams to try to diagnose, why am I getting a bad test on this phantom load compared to a customer load? And so we're able to re-examine not just the meter, but the entire installation. So meter performance under real-world conditions. Large errors can occur in the calculation of VA and VARs when my power factor does not equal 1. And so the problem is this: there is no official definition in the presence of harmonics. We know there are harmonics, but there's still disagreement about how to measure it and what might be allowable or not. Different meters may implement different definitions. in dealing with the harmonics. And the variations in these scenarios can be as large as 15 to 30% between two meters, both of which are what we would call working properly. So this is still an area that's being developed. We can measure the harmonics, but what you want to do with it, that might be up to your utility and how to handle it. Another big one is the clerical errors. As we saw, it was almost 40% on the pie chart. There's no amount of testing that can detect clerical errors. This has to do with you guys in the field. And you're going to look at that at the CT nameplate and the PT nameplate. And there may be I keep saying rating factor, but that's not the one I'm looking for. What is it, Chris? What's the word I'm looking for? Not that's it, billing multiplier. I lost my mind for a second there. Maybe for some reason, right there in your 3 series, it says that this site that you've been to before, it has a billing multiplier, for instance, of 3. And you walk up and you go, oh yeah, this is normal, everything is normal, everything's checking out. But you look at that nameplate and you notice that the billing multiplier is not 3, it's 5. Oh my goodness, do I have a problem now? Because all this time I've been multiplying by 3 and it should have been a 5. The 3 series and the meter, it's not going to tell you that it's supposed to be 5. This is the clerical part of the job. This is where we transfer the right numbers in the right places. So only care and careful procedures will eliminate these kinds of errors. Okay? Clerical errors can go on undetected for years and cost the customer or the utility hundreds of thousands of dollars. So these are the kinds of things that you have to pay very special attention. Make sure that the billing multiplier that you have in your 3 series matches the multiplier that's on the nameplate. Make sure that the ratio is the same on both devices, and so on and so forth. Not all problems are natural. This has to do with theft. The current recession has dramatically increased incidences of revenue theft. There are all kinds of opportunities for people to mess with, especially with the CTs. There are instances of, there was someone one time that was going around in particular to gas stations and offering to reduce their power bill. I said, I can help you reduce your power bill. It won't affect your power at all. Everything will be fine. Your pumps are still going to work. Your cash register is still going to work. Your lights are going to work. And what he was doing was he knew his way around a site, and he had a ladder, and he was able to get into the CTs, and he added a few wraps of wire into the CT. Well, what did that do? It added burden. The CT was now overburdened. He was adding turns. And so now the CT was overburdened, and everything was still working properly on the other side of the meter, but it was no longer billing correctly because of the added turns in that CT. Well, nobody knew about that. They knew that the numbers were coming back to the office, and the bill was decreased, and somebody said, this needs to get checked out. This doesn't look right. They went to the site. Everything at the meter looked right. Somebody finally gets in a bucket or a ladder, and they went and they finally found there were extra turns, and nobody knew about it. They removed those turns. They made everything right. They removed the extra wiring, and everything came back into order again. Someone might put a knife blade and try to bypass the meter. So self-contained services. You want to have what they're looking for is a diversion prior to the meter or meter bypassing. Transformer rated services. There could be diversion prior to the CT or tampering with the CT itself, tampering with the PT or tampering with the meter wiring. So these are things, especially right now because of the COVID-19 situation, you really want to be on the lookout for these. It's not going to be in the meter, it's going to be around the meter. They're trying to bypass the meter. They're trying to change what the meter sees, okay? And so estimating errors, uncertainty when nothing is wrong, okay? So what we want want to talk about is what is the best case scenario, okay? We know that the meters have a 0.1% or 0.2 or 0.5% accuracy class. The CT itself is a 0.15, or a 3%, or probably a 0.6%, okay? And the PT is a 0.3%. Okay, so what that means is there is error that we cannot avoid in all of these instruments. So my worst case error estimate means if I add up that 0.2% and that 0.6% and that 0.3% from here, that adds up to 1.1%. So if everything is working correctly, about 1% is the worst error that we should find. But what do we do when 0.5% to 1.1% accuracy is not enough? Well, we have a couple options. One is the meter. We can choose a 0.1% accuracy class meter and test for accuracy under the customer load conditions. Okay, remember, customer load is different from the lab. That's different from back at the office. Okay, so I want to test under customer load conditions. My CT, I want to use an accuracy class of 0.15S. We also have these extended range CTs that are really taking over because I can use the same CT in a number of different situations, and it relieves the burden from having from inventory back at the office, and it relieves how much I have to learn on so many meters. I know the same thing applies to the same meter all the time. I want to reduce the burden well below the rated levels. And on my PT, I want to use accuracy class of 0.3 or even eliminate the PT if possible. And so with the best equipment, I can get a 0.1% plus 0.15% plus 0.3% comes out to a 0.55% error. Okay, so be sure and send in your questions, or if you have any comments, remember that you can set up, if you call into the office here, you can make an appointment to set up further teaching on our training benches for your specific questions or specific meters that maybe we haven't addressed in these classes. And that is the end of our teaching today. I want to remind you to please be safe out there. Make sure use all your PPEs and use all your training in all your circumstances. God bless you. Thank you for tuning in.